Good morning, everyone. Today we're doing Unit 6, Lesson 6 review. So we're just going to wrap up our discussion on vectors. So let's start by talking about what makes up a vector. So we're going to state the difference between distance and displacement and provide an example of each. So distance only has magnitude. We talked about that in the first lesson. Distance only has magnitude. For example, when we're talking about kilometers, right, we could say 10 kilometers, but that just tells us the length, right? That doesn't tell us which direction the 10 kilometers are going in. Whereas displacement has both. So displacement has magnitude and direction. So if I wanted to use that same example of 10 kilometers, I might say that we're traveling 10 kilometers south 20 degrees east, right? So we'll get into those bearing measurements, but that gives us magnitude and it gives us direction. So vectors are a quantity made up of both of those things, made up of magnitude and direction. So essentially, vectors measure the displacement of something, right? Because displacement is both magnitude and direction, and that's what vectors are a quantity of. So let's first talk about the magnitude of vectors, and then we'll talk about the direction of vectors and practice those a little bit. So vector AB has a magnitude of whatever the absolute value is of AB, vector AB, right? If the length of AB is a -4, then the magnitude is 4. So whatever the absolute or the positive version of that is. So vectors can be represented as a directed line segment with magnitude and direction, as we mentioned above, if the horizontal and vertical components of the vector are given. Okay, so we'll look at, again, breaking down a vector into its vertical and horizontal components and how that helps us determine the magnitude of it. When we're talking about the direction of vectors, vector AB direction can be determined by using trigonometry. So remember, when we're trying to determine the direction, we're looking for the angle between two vectors. So whenever we're trying to find an angle of something and we're using trigonometry, we could use SOHCAHTOA for right triangles. If it's not a right triangle, we would use sine law or cosine law. Okay, so we use any of those three things within trigonometry to find the direction or the angle between two vectors. Okay, and the direction can be represented by two different types of bearing. The first one is a true bearing. I'm going to put true in brackets, because sometimes we just see it called bearing, but it can be represented either way, or a quadrant bearing. Okay, so a bearing, remember, is an angle measured clockwise from the north. And it's always 3 digits. So an example of this, if it's only really a 2-digit number, we put a 0 in front of it. So 0, 48 degrees, or if it's already a 3-digit number, like 172 degrees. Okay, those are bearing angles. A quadrant bearing is our other way we can represent the direction of a vector. So a quadrant bearing is an angle between 0 and 90 degrees measured east or west of the north-south line. So remember, we always start one of the parts of our angle that's made up when we're talking about a quadrant bearing is either that north or the south line of a compass. So an example, we could say like the one we gave above, south 20 degrees east, north 40 degrees west, right? So it's always representative first by a north or south, and then whatever the angle is as we moved east or west from that north or south line. So let's look at some examples. We're going to sketch these diagrams, or sketch these vectors rather. They're providing with us the horizontal and the vertical component for each of them. So it's a sketch a diagram and determine the displacement, which remember displacement is the magnitude and the direction. So let's just make sure we all remember that. So displacement is the magnitude and direction of the following vectors given their components. So the first number, is going to be their horizontal component. And that second number is going to represent the vertical component. Okay, so for vector EF, let's first plot that. So EF is over 2 and down 4. So over 2, down 4, right? So the vertical component is 2, and the horizontal component is 2, and the vertical component is -4. So from that start point, we connect to that end point to represent that vector, and that's going to be EF. Okay, let's just draw them all on here, and then we'll go back through and figure out their magnitude and the direction. So the next one, GH, is at -3 and +5, so that's the vertical component, and then we put a point at that end point. So from the beginning to the end of that vector will look something like that, and that is GH. And then finally that last vector is 0, 4. So we don't move anything over on our horizontal, but we do go up 4. And then we'll connect those with a straight line. And that is IJ. Okay, so let's go through and we will determine the magnitude and the vector for both of these. Sorry, the magnitude and the direction. So first let's do the magnitude. And then we'll take a look at the direction. Okay, so our first one, if we need to find the magnitude, we're basically finding the third side of this triangle, right? So we know that this side of the triangle is 2, and this side of the triangle here is a length of 4. So to find that third side, which we can represent with any variable, C, X, R, doesn't matter, we need to find that third side. So we will say that C squared equals 2 squared plus 4 squared. So C squared equals 2 squared is 4, 4 squared is 16, so that is 20. Now we take the square root of that, and we should get 4.5. Okay, if we're wanting to find the direction, we need to take a look at what trig ratio we can use. So we have a right triangle here. If I'm trying to find the direction, I'm trying to find this angle right here. It's always the angle made with the horizontal. So I know my opposite side and my adjacent side. So I'm going to do the tan of my opposite side, which is 4, over my adjacent side, which is 2. So the tan of theta is equal to 4 over 2. And then we isolate that by taking the tan inverse. And we should find that theta is equal to 63 degrees. Okay, so we could represent this a couple ways. We could represent this as a true bearing, or we could represent this as a quadrant bearing. So let's show both. So remember, a true bearing starts at that north line, and it moves clockwise from that north line all the way to wherever that angle is. So that means I'm moving 90 degrees and then another 60 degrees. So my true bearing, or my bearing, is going to equal 90 plus 63, which is going to be 153 degrees. My quadrant bearing, well, if we label our axis with our north, east, south, and west, we can see that in this case, we are closest to our south line, okay, and we're moving in an east direction. But we don't have that angle between. We have the angle between the east line and our vector. So we need to find that angle between my vector and my south line. So we're going to do 90 minus that 63, which equals 27 degrees. So we'd say on our quadrant bearing we have south 27 degrees east. All right, so that's the magnitude and the direction for that first vector. Go ahead and pause the video and see if you can work through the magnitude and direction for that second vector. Okay, there's your solution for your second one. So when we use Pythagorean theorem, we find that the magnitude is 5.8, and then we can determine our bearing is 329, or our quad bearing is north 31 degrees west. Let's look at this last example. This one is a little bit more straightforward. If we do our magnitude is our x squared plus our y squared. So in this case, we'll represent that with c again. Our x squared is 0, and our y squared, 4 squared. So we get c squared equals 16, or c equals 4. Okay, so for our bearing, remember our bearing is that clockwise rotation from the north part of our compass. Well, we don't rotate it all, so we could just say our bearing is 0 degrees. And our quad bearing, remember, it's always measured from our north-south line, so this is for sure on our north line. But again, we don't move any direction east or west, so we would just say that our quad bearing is directly north. So that one's a little bit shorter, straightforward. All right, let's continue. So we're going to look at, see if we can identify some bearings from a diagram, and then if we're given the bearing, can we draw it on a diagram and identify the other bearing? So we'll try one together, and then we'll see if you guys can do one on your own, or the next two on your own. So we have a diagram here, and if we wanted to represent this first as a bearing, we have to start from our north line and follow that all the way down to wherever the vector is. So we went 90 degrees clockwise, and then a little bit more from there. So we have to determine what's this piece in here. Well, this piece in here is going to be 90 minus that 34 that's represented in that quadrant. So 90 minus 34 equals 56 degrees. So our bearing is going to be 90 plus that 56. So 90 plus 56 is going to equal 146 degrees. Okay, and our quadrant bearing, remember, is always representative of our north or south line. This one is closer to our south line, and then it moves 34 degrees in an east direction from there. Okay, so pause the video, try the next two on your own. Okay, so there's the solution for the next two. The second example there, for our bearing, we moved clockwise from that northern part of our compass, 241 degrees. So that's our bearing, nothing to calculate there. For the quadrant bearing, we have to determine what's the angle between the vector and the north or south line. So this is closer to our south line, so we need to determine the angle that's made up between the south and line and the vector. So what's the angle from here to here? So I took 180 because that's how far we had traveled to get to that south line, and subtracted it from that 241 to give me that angle, which is 61. So we can see that it's south 61 degrees moving towards the west. Okay, and then the last one, 42 degrees in a northeast direction. All right, we're going to look at a few problems involving vectors, and that'll wrap up our review for today. So problems involving vectors. We can use vector addition or vector subtraction. To find the magnitude of the resultant. So by adding two vectors together or subtracting, we can find the magnitude of that third side, basically of a triangle. Then we can use trigonometry to determine the direction of that resultant. So just like we said on the first side of this note, right, that SOHCAHTOA, sine law, cosine law. The direction can be expressed again as an angle relative to one of the vectors or as a quadrant bearing. So if we're not necessarily on a northeast southwest compass, we might express the vector direction relative to another vector. So let's look at some examples. So Stephen drove 7 kilometers west, then 18 kilometers north. So let's draw that on a, since they gave us directions based on a compass. So Stephen drove 7 kilometers west, and then he turned and drove 18 kilometers north. It says calculate the magnitude of the displacement vector to the nearest tenth of a kilometer. So once again, the resultant is just the connection of those two vectors. I'm going to put some arrows on there because he moved west and then north. So the resultant is the connection between the start of the first vector and then, or the tail of the first vector and the head of that second vector. Okay, so it's moving in a northwest direction, our resultant. So we can determine the magnitude, call it R, by using Pythagorean theorem. Okay, so R squared is going to equal 373, and we take the square root of that, we should get 19.3 kilometers. The next question says determine the bearing of Stephen's car to the nearest degree. So bearing, remember, is just our true bearing. If you want to figure out your quadrant bearing, you can as well, but this is just asking for our bearing. So that bearing is always the angle that's made with the horizontal. So we're trying to figure out theta. So if I'm trying to figure out theta, I have my opposite side and my adjacent side. So I'm going to use the tangent ratio. My opposite side is 18, and my adjacent side is 7. So we take the tan inverse to isolate for theta. And we find that theta is equal to 69 degrees. So if we wanted to represent our true bearing, we have to understand that we start from our north part of our compass and we move in a clockwise rotation until we get to that vector. So we're moving 90, 180, 270, and then plus that angle we just found of 69 degrees. So our bearing is going to be equal to 270 plus 69, which equals 339 degrees. Okay, last part, is the distance that Stephen traveled the same as the magnitude of the displacement? Well, let's take a look at this. So the amount he traveled 7 kilometers west, then 18 kilometers north. So he traveled 25 kilometers, but the displacement, or the magnitude of the displacement, is 19.3. So no, they're not the same. And we can say no because the magnitude of the resultant is a direct line segment. From the tail of one vector to the head of the other. Right, we're drawing the shortest distance possible from where we started to where we ended. Whereas the distance he traveled, he went around some corners, right? He didn't take the direct line segment there. Okay, let's look at one more example. Our rocket is propelled at an initial velocity of 140 meters per second at 78 degrees from the horizontal. So remember, we said that we could represent it in a northeast-south direction, or we could represent angles based on another vector. So we're representing this angle as 78 degrees from the horizontal. Determine the horizontal and vertical components of the velocity. All right, so if we have a rocket's propelled 140 meters per second And if we were to compare this, let's say with the ground, right, or some horizontal, the angle it makes with the horizontal is 78 degrees. So they want us to determine our horizontal vector, which we'll call x, and our vertical vector, which we'll call y. So we have one angle and one side. We should be thinking about using SOHCAHTOA to determine those other side lengths. So if I want to find my horizontal, let's say first, I'm going to use cosine. So I'd say the cos of 78 is equal to that x vector in my adjacent side over my hypotenuse. And then I'm going to multiply the 140 over to the other side. And when you do that, you should get that x is equal to 29.1 meters per second. And remember that if this was on a compass or we are on the negative side of our Cartesian plane, it's always going to be the absolute value of whatever our horizontal is, because we're looking for the magnitude of it. If we wanted to find that y length, I'm going to use the sine of 78 degrees. It's going to equal my opposite side, which is y, the absolute value of it, over the hypotenuse, which is 140. So we multiply that 140 over to the other side. And you should get that y is equal to 136.9 meters per second. Okay, it says determine the height of the rocket 20 seconds after liftoff. So we know that we have our vertical speed, our vertical velocity. So we're going to use that information to help us here, because we're trying to figure out the height, which represents a vertical distance. So if the rocket is moving 136.9 meters in 1 second, how far has it traveled in 20 seconds? So the height is going to equal that velocity times the amount of times we're looking at it for, so times 20 seconds. And you can see here that when I multiply 136.9 meters per second times 20 seconds, the seconds will actually cancel each other out. So all we're left with is meters, that's great because we're trying to figure out the height of something. So we'll get 2,738 meters. Okay, one more example, and then we'll be all done. So a boat travels 5 kilometers north, 60 degrees east, and then turns and travels 3 kilometers north, 10 degrees west. Find the resultant displacement of the boat. So this does use some compasses. So we're going to start by representing each direction as they give it to us. So a boat travels 5 kilometers northeast, we start with. So let's draw a compass down here. And we are traveling northeast, something like that. And it's on a bearing of 60 degrees from our northeast line. So northeast that way. And we are 5 kilometers. Okay, then it turns and travels northwest. So from this point, if I was to draw another compass with that going right into the origin of my new compass, it's going to turn and travel northwest. So now from here, it's going to turn and travel in a northwest direction. Okay, make sure we put some arrows on those so we can see the direction it's moving. It's going to be northwest 10 degrees, and it travels 3 kilometers. Okay, so it says find the resultant displacement of the boat. So we went one way, and then from the start of one vector to the end of the other vector, that's going to be our resultant. So some information we can determine here. Remember that this 60 degrees here is an opposite angle with this angle here, right? Those are opposite angles, so those are equal. So we're going to have 60 degrees here as well. So if we're wanting to find this angle, we can do so now because we've essentially created a straight line. So if we were trying to find this angle, we have 60 and 10, and then this angle is going to make up the rest of that straight line, which is 180 degrees. So we can say 180 minus 60 minus 10, which is going to equal 110 degrees. So this is 110 degrees, and here this angle. Okay, so now I'm trying to determine something about my resultant. I have our side, angle, side. So I'm going to use cosine law to find that third side. So we have to remember the pattern for cosine line. So we're going to have r squared is going to equal to the sum of the squares of the other two sides. So 3 squared plus 5 squared minus 2 times those same sides multiplied by the cosine of the angle across from the side we're trying to find. So the cosine of 110. So when we calculate that, we should get 44.2606043. Remember, we don't want to round until the end because it'll change our answers. So you'll get 6.7 kilometers. All right, and that's going to represent the magnitude. Remember, with displacement, we want magnitude and direction. This is our magnitude. Okay, now if we want to work towards finding our bearing, we can find this angle of our triangle. Okay, I'm just going to erase this so we can make it a little clearer. I feel like there's not enough space there based on my drawing. But if we were to draw kind of a crooked compass. If we were to draw this compass like this, right, my quadrant bearing is going to be that distance from there to there. But we know that this whole distance is 60 degrees. So if we find this angle within the triangle, we should be able to subtract the two numbers to find that quadrant bearing. So if I want to find this angle, which we will call theta, I'm going to use my sine law now because I know that r, we just calculated r equals 6.7. So I can use that information to set up my sine law. So I'm going to do the sine of theta over 3 is going to equal the sine of 110 over the side opposite that, which is 6.7. So I'll multiply the 3 over to the other side. So I'll have 3 times the sine of 110 over 6.7. And then we're going to take the inverse to move that sine over to the other side of all of that information. So theta is going to equal 25 degrees when we calculate that. All right, so if theta is 25 degrees, but we need that space between the 60 and that 25 degrees. So the bearing is going to equal 60 minus that 25, which is 35 degrees. And we can see that that is in a northeast direction, right? So it's going to be north 35 degrees east. So let's just wrap it up with a therefore statement. So therefore, the resultant displacement is 6.7 kilometers on a quadrant bearing of north 35 degrees east. Okay, and that's it for your notes for today.